In this lecture, we're going to introduce the ideas of virtualization. So let's start with virtual machines. So a virtual machine is, first of all, it's a software construct, but it exposes the resources of CPU, memory, disk, and network connection to any software that's loaded into it, and it makes it appear to the loaded software that it's executing on a physical computer. And a virtual machine runs under the control of a specialized operating system called a hypervisor. And there are two types of hypervisors. One runs on bare metal, so you have the host computer, the hypervisor, and a collection of virtual machines, each with their own operating system and their own set of applications. The other type of hypervisor is type 2, sometimes called a hosted hypervisor. And here the virtual machine part of it is actually an application as far as the operating system is concerned, and it has other applications in it, but within there is the hosted hypervisor, and it has a collection of virtual machines, each with their own operating system and own applications. Again, the resources that a piece of software inside a virtual machine sees are the CPU, memory, the disk, and network connections. So for discussion, how are the actions of one virtual machine kept separate from the actions of another virtual machine on the same host, whether it's type 1 or type 2? And you can think of it as one resource at a time. So, for example, how does it write to a disk? How does it write to a network? How does it get messages from the network? How does the message from the network know that this is a virtual machine that is listening for that? Uh, then how is a virtual machine created? How is it booted? Okay, these are all, if it looks like it's a bare metal machine, bare metal machines have to be booted. How are virtual machines booted? And so now let's move on to images. So a virtual machine image is a set of bits on a disk. Remember, bits are bits, or from over a network. So you can read them, you can write them, you can send them on the network. And it contains all of the software directories and data from the virtual machine that created that image. So that suggests what I'm about to say, that a virtual machine image is created by building a physical computer with all the software you want, or building a virtual machine with all the software you want, and then writing the contents of the memory to a disk file, and then maybe sending it over a network. Maybe you don't write it, you send it over a network. And then you create a new one by reading an image. So you have a virtual machine, it reads an image in, and now it's loaded with software. And so here, this is a picture that does that. So there's a VM that's used to create the image. It writes all its bits to a disk in this example. And then there's another virtual machine which doesn't have any software loaded, and it reads all the image into memory. And that's all managed by the hypervisors. So let's talk about timing. So let's suppose the image is 8 gigabytes, not that big. Uh, a reasonable network speed is 1 gigabit per second, and that's what it's rated. That's not actually what it is. And there are 8 bits per byte. So networks are rated in bits per second. Images are measured in bytes. So moving an 8 gigabyte image will, in theory, take 64 seconds, 8 bits per byte. Uh, it turns out that networks don't run at their rated speed. They run around a third of the rated speed. And so actually transferring an image takes around 3 minutes with that speed of network. And then you still have to boot it. Okay, so that takes some time too. And so one discussion question, can a VM image that you created on the Google Cloud be moved to the AWS cloud or vice versa? And so now let's go to containers. So a container is another software construct, but it's intended to be lighter weight. Uh, 3 minutes is a long time to wait for something to happen these days. And so you want to have things that happen faster, and those are containers. You still have the most of the advantages of virtualization. So you have isolation of actions, and the image transfer time is going to be much less, and the startup time will be much less. So a container has images. It's an executable image, and a container packages a service and its dependent libraries. And so it's self-contained, and it runs under the control of a container engine. The interface between containers and container engines has been standardized. So if you build a container with one build system and you run it on a runtime engine from a different vendor, it works. Okay, so containers are portable. And containers are isolated in terms of address space. They're isolated in terms of disk usage. They're isolated in terms of processors. And they're mostly isolated in terms of network. So we will talk about the differences in network usage in the next lecture when we talk about networks. So the executing container sits on top of, so it has applications inside it. It sits on top of a container runtime engine, which in turn sits on top of a host operating system, which in turn sits on top of a bare metal or a virtual machine. And it contains all its dependencies, again, so that it's self-contained and you can move it around and run it. Containers can be incorporated into layers. So consider the LAMP layer. LAMP is the LAMP stack. LAMP is Linux, Apache, MySQL, and PHP. And the PHP part is the top layer, and that becomes important in a minute. But each item can be made a separate layer. Now let's suppose you want to update something. So you've changed your PHP. That's the top layer. You can move just the top layer without having to move any of the other layers. And so the amount of data that you're moving is really just your PHP program, which is relatively small compared to everything else. And so that's one reason why containers can be invoked a lot faster than virtual machines. You don't have to move everything. You just move the operative part, if the operative part's on top, and it can execute. If you're going to want to move one of the lower layers, then you also have to move the things on top of it. So if you compare virtual machines and containers, virtual machines virtualize hardware, containers virtualize the operating system. Virtual machines take minutes to transfer over a network. Containers can be transferred in milliseconds, again, depending on the mechanisms you use. VMs are monitored, started and stopped by the hypervisor. Containers are monitored, started and stopped by the runtime engine. And we'll talk a lot about that in a subsequent lecture. So discussion questions. Uh, how are the actions of a container kept separate from the actions of other containers on the same host, on the same runtime engine? And again, think of it in terms of resources. How does a container write to the disk? How does a container write to the network? How does it get a message from the network? How is a container created? These are the same questions, virtual machine. How is a container placed into execution? How does the container management system know that only the top layer has changed? So containers are stored in repositories, and the repository is similar to a version control system. So it's accessible if you have permission. It's got a push-pull interface, push a new version, pull an old version. And images can be tagged with version numbers, so you can pull version 3 or you can pull the latest version at your choice. Docker Hub is a publicly available repository. It's open source, so you can use the publicly available version of Docker Hub, or you can put install Docker Hub in your own organization and keep it just for images within that organization. So if you think about how the development workflow would go, one team would develop an image, uh, one member, and then another member of the team wanted to get the latest image, and it would pull it, or another team wants to get the latest image, and it could pull it. And so that image is now shareable in the same way that code is shareable through a version control system. So a discussion question: are there container repositories other than Docker Hub? Why would you choose one over the other? And finally, let's talk about serverless architecture. So again, remember that you only have to, if you're using layers, you only have to move the top layer. So let's use an example of PHP. PHP is interpreted, which means that the bottom layers include the interpreter. And so if you have a image sitting around, your cloud provider keeps a pool of these images, and you feed it a PHP program. Again, it'll be fast. Then the cloud provider can invoke that. Your PHP program will control what happens, and the program is executed immediately. So the only thing that has to be transferred is your PHP file, which is relatively small. And so a more formal definition, a serverless architecture consists of a pool of servers with container runtime engines and possibly portions of a stack, a stateless container with no dependency on your other code, and then the stateless container, if you're not using the layered mechanism, the stateless container can run directly on the runtime engine. That's all set up. Since the container has no external dependency, it can be executed directly by any runtime engine, and including the runtime engine that your cloud provider has. This is also called function as a service, FaaS, although I haven't seen that used very much. So the container is deployed and activated when a message arrives for it. So you send a message, you say, I want this message to go to a particular container. The infrastructure knows where that container is located. It pulls it in. Again, the serverless architecture model. It pulls it in. It has a pool of runtime engines, so it allocates one, pulls in the container you want to execute, puts it on top, and deploys it. So this runs in milliseconds, so you can deploy a container in milliseconds rather than in minutes. And AWS restricts you to doing this one message at a time. And so then it gets freed so you can use other members of the pool. And people spend a certain amount of effort trying to make sure that their container stays there. They don't have to spend the milliseconds, although milliseconds is fast. So a more complicated example of how you might want to use it. You run a subscription service, somebody signs up for it, you want to send them an email that says, welcome new customer, uh, here's some information, and you have a container which generates an email message. So it knows how to send an email message. It knows what the content of the email message is. It gets two parameters. One is the email message for the recipient, and one is the name of the customer. And so the container is stateless. It doesn't have any memory. You can just load it and execute it. And so the general service that you're running sends a message saying, generate an email, a welcome email to this container. The infrastructure understands what it's doing. It routes that message to an instance of the container that generates the email message, which is going to be serverless, and the email message generates the email message, and then it stops. It's done its job. So discussion questions. How does a cloud provider know that the a certain container is intended to be serverless. What are the restrictions on serverless containers? So I talked about them being stateless. Are there others? Okay, so that's the end of this virtualization layer lecture.